If you open that guide page called PDE models, that's a good base for us to look at everything from.
Okay, good. Okay, for people joining this live stream, we are talking about PDE models and the effort to make specific PDE models of particular kinds. Oh, come on. Why does it do that? It was supposed to be set to not do that.
So,
okay, now we talked last time about some things that were not okay, but I think, have those been fixed now where we're starting off with things like diffusion term and so on?
Yeah, so
yes, good.
I've added the Laplacian term, Poisson component, Helmholtz component, and wave component.
I like it.
Good. Schrödinger is in the making, is not finished yet, but I'm working on that.
I like it.
Devendra suggested to also add correct de Vries. I haven't looked at that yet. One concern there is that this is a higher than second order spatial derivative, so we can't do Wolfram right away.
I think the KdV is a mistake.
I wouldn't bother with KdV. I think KdV,
yeah, I don't think it's right
special
either.
interest.
Okay, yeah. Good. Then we'll remove that, and
I would put it in the function repository or something for now. Schrödinger should not have an E in it.
Okay.
Our conventions should not have an E.
Okay.
It should have an Ö.
Well, I know it should have an but we don't do Ers in function names.
I'll remove the, okay.
Same as Grosvenor is with a
I got it.
Okay, so let's take a look at diffusion term here. Let's skip this kind of nonsense.
Okay.
I mean, it's amusing, but I just don't think that's a...
Okay, I'll remove it, no worries.
Yeah. I mean, there's a separate kind of page, perhaps.
I think it's very important for these other ones because a modeling language, the point of a modeling language is to bridge real world and model world.
I know.
My understanding was that Stephen was talking about the image, right? Not the graphics above that.
No, not the graphics above that. That's okay.
Yeah, okay, good.
No, the image is not intended to be there. That's an idea.
Yeah.
Or an illustration.
Yeah, I'll remove it.
Well, okay, fine. I mean, look, I think showing... Listen, I think showing what happens to a Gaussian under the diffusion equation, that will be useful to show. I mean, alongside this picture, show a Gaussian, show it diffusing down. I mean, I think that would be helpful. I mean, maybe that's what you have as the first example here. Do you? No, that's what I want to see as the first example. Okay, I want to see something where you just start off with a, some little,
got it
step, and then it decays. And makes a Gaussian. I also think it would be useful in properties and relations. I hope you have, in cases where there is an analytical solution, I hope you show how that corresponds.
Not yet, but I'll add it.
Yeah, that's important. And I think it's also important now, presumably you can use this. Actually, wait a minute. In cases where there's an analytical solution, even in the basic examples, you should show that. Like you should show how you can use diffusion term in, desolve.
Well, that's not, I need to talk to the vendor about that because those operators are inactive and I'm not sure desolve can handle it.
Then he needs to make it handle them.
Yep.
Sorry, that's part of
I've talked to him about that and I think it's in the making, but I don't know the latest.
So fine, but that's an important thing to make happen, okay?
Yeah.
Because that's what it means to have a good integrated interoperable system.
Absolutely.
We're well aware. So it's been informed, but it's just not, I don't know far.
Okay, all right. But I mean, so it is correct, is it not, that something like this, if I look at the detailed form of this term, right? I don't know what that -1 thing is here. Why is that so braced up, that -1? Do you understand my question?
Not really, no.
Okay. This is a one-dimensional.
It's a matrix. Term. It's a matrix, right? Okay.
Why? It's a one-dimensional diffusion equation here, isn't it?
So because it's a dot product. It's the dot product with the gradient. And if we have two spatial dimensions, it's going to be a 2 by 2 matrix.
Okay, but why isn't it just a vector dotted into the gradient here? Why isn't a matrix dotted into the gradient? Do you understand what I'm asking? This is a scalar quantity, right? U of
so
x
it
is
could
a
be
scalar.
multiplied with times. But if we want to use the consistent dot in all dimensions, then it has to be a matrix.
Okay, but wait a minute. So this thing here, gradient there is a vector, correct?
Yep.
Or not?
Yep.
Okay, so a vector dotted into a matrix gives a vector, right?
Correct. Yeah.
Oh, I see. And then there's a div. Yeah, then there's a div. Okay, I get it. Then that gives a scalar result.
Yeah. Right.
Okay,
correct.
so I think it'd be useful to show in this diffusion term thing here, I think it'd be useful to show this being used symbolically as well. That is, given just to show that if I put in e to the minus x squared, that I get, like let me just try it here, okay? So what I should be able to do is say, okay, so then we're also explaining some other things here. So let's say I give this thing here, and I put in there e to the minus x squared. Okay, so now it does that. Okay, so now I say activate that, and I get this. And now explain how this works. I've got diffusion equation. Okay, I don't really understand this.
Do you want the coefficient to be the exponential? Because you've made the dependent variable with the exponential. So
no, I'm saying that u of x, the solution u of x, is e to the minus x squared.
Okay, yeah, okay.
Okay, so now why isn't this working? Why doesn't this come out to just be something proportional to e to the minus x squared? Do you understand what I'm saying? Diffusion equation is d thing by d time. Oh, maybe I need, maybe what I need to do is, what is the right solution? X squared over t, right?
And then you need to add a t now for the time-dependent component, right?
Well, so then what I want to do is I want to take this and I want to say derivative of that with respect to time. If I'm not mistaken, is that correct? Okay, what happened here? Well, in any case, I think you need to give this in the example.
Yeah, I know I see what you want, yeah.
Right, so just to show people that this isn't an alien creature.
Yep.
This is just a way, I mean, in other words, okay, so here's what I think we should do, right? So, like, for example, if I were to just take that diffusion term there, take the original diffusion term from here, and I were to just say, let's try it. Let's activate that, okay? And then say, magnificent. Okay, that right there, that's very useful to see.
Okay.
Right, and then to say, okay, fine. Yeah, in fact, that's what I would like to see very, very first. You can see this, and then say, I mean, basically just put in after that activated percent.
Yep, good.
And similarly here, because this is again going to show, what really is that.
Okay.
In the simple case.
Yep.
Right. You just say slash. Why did that? I don't understand that.
Well, so the kappa is replaced, but it's a constant.
Oh, I see. It's equal to 1. Yeah. So if I
make
set
it
that
x
to a, well, if it's position dependent,
for example, yeah.
Okay.
There you go.
Magnificent. Okay, fine. Okay, now what is the minimal syntax for this diffusion term? Do I have to put that x in braces? What am I doing here? So what I'm putting in here, what is the actual form here? So this is x. I see. Okay, so it's the dependent variable and then the independent variables.
Correct.
Okay.
Yeah.
Okay, so presumably we should support the case without braces around the x.
For a single independent variable, okay?
That is what I mean, yes.
Yeah.
Okay, so I mean, what is really nice about this is let's just write out, we'd be saying du of t and x. Now, I don't understand why you'd say u there, because I would expect it would be u of t and x that we would be giving, right? Why are we just giving u of x here? Am I making sense?
Yep, you can add the t. It's not documented though, because this operator is in principle a stationary operator. So you t comma x.
Mm-hmm.
I mean, do the comma t close plus the diffusion term u x comma t.
Well, comma t plus.
Yeah.
New tx.
Yeah, correct.
Comma, and I'd like to just say comma x here, but
well, that's not working yet. But yes, yeah.
Okay, there it is.
And you need to activate that again because
I understand.
This works fine already. Yeah, there you go.
Great. Great. That's exactly what I want to see. I mean, you see this kind of thing, particularly with more complicated equations.
Yep.
That's beautiful.
Good.
And that we should write that out somewhere here. Just say that is the diffusion equation.
Yep.
That's very nice. Okay, let's do that with a more sophisticated equation.
You could add another term, for example, like a source term to make a Poisson type equation.
Now, when you say source term, there are many source terms in the world.
Yep.
I don't think it should be called source term.
Yeah.
What should it be called? What is it, in fact?
So it's basically, typically, if you have an equation left-hand side, right-hand side, it's what's on the right-hand side. And typically, it's independent of the dependent variables, but it's more general than that. But that's what's typically what it is, yeah.
So it's a forcing term. It's an inhomogeneous term.
Yeah.
So Vladimir on our live stream is pointing out that a more generic way of describing PDEs is with the elliptic, hyperbolic, parabolic characterization. But the problem with that is, as I understand it, is that there is no, you say, okay, it's an elliptic PDE. Well, okay, so a question.
If I change character, they can change character over space.
No, I understand, but I'm asking the question, is there a generic parameterization of an elliptic PDE? No, because elliptic is a description of the way the characteristics work, is it not?
Yes.
Yeah. Well,
so that's
Stephen, we have a generic parameterization of the PDEs, and that's what that's what our finite element method solves, is that particular generic parameterization.
I don't understand that. Can you make a comment? Can you explain that?
Okay. Well, all of these building blocks go into a particular second order spatial PDE, say, okay, which is typically elliptic. So these building blocks are to form those things, but we have that.
Have what?
We have a very basic form that we solve for the finite element method.
So what is that form?
Where's a good place to see that, Oliver?
So
but wait a second.
Building blocks just says model partial differential equations of the form, and that's the complete form.
So why don't we just have a parameterization of that?
It is there.
No, I understand. Why don't we have a function which just takes, alpha, beta, gamma, c?
I see. Okay.
But
we could, but then we wouldn't have basic stuff like diffusion term.
No. You're not understanding
additionally.
What I'm saying.
Yes. In addition.
What I'm saying.
Good.
What I'm saying is, okay, so in fact, this is a good point. Okay, so if I trivially look up an elliptic PDE here, right? This is the form, this just has a bunch of coefficients, right?
Yeah.
And I'm not sure how much it helps us to have, it saves some typing.
It would be useful to have because especially some customers have problem with the typesetting and things like that. So it's like, I think it would be useful to have, and I think I'm going to add it anyways.
All right. Okay. So why don't we add it in this form, right? As opposed to
no. We don't.
No, I think the matrix is the right way to do it, Stephen.
Yeah.
What matrix?
Well, that's that diffusion coefficient is a matrix, right? And that generalizes to 1D, 2D, or 3D easily. Whereas this form happens to be a 2D form.
Yeah. Okay. So explain to me what the general form is.
So basically, C is a matrix. Everything that you see that's a Greek letter is a vector, and everything else is a scalar.
So you're saying this works in arbitrary numbers of dimensions?
In principle, yes.
But I don't understand why this thing isn't just a general, look, if it's a linear function, right?
It must not be.
What's that?
C can depend on U, on the dependent variables. It must not be linear.
Okay, but then it need not be linear, you mean?
It need not be linear,
okay.
yeah.
Yeah, okay. But in general, why aren't we just having a thing where, I don't understand why there isn't a trivial matrix here to give, which is, am I confused? No, a tensor, in fact.
Yep.
And the tensor is basically just the components are, the one, the x derivative, the y derivative, the z derivative. Am I confused here? And then we simply have, or is it just a, okay, this is a second order. Are we talking second order, or are we talking other things? We're talking second order.
For a single dependent variable, we're talking a matrix, yes.
Yeah, so a second order, a matrix, which just has those coefficients in it. So I don't understand why we don't just say, I mean, we could just say linear, I don't know, linear PDE term, and then what we give is a matrix, or in general, if for higher order equations, in general, a tensor. For second order, it will be a matrix. For third order, a tensor. And we just give that. And then we give that matrix of coefficients, and then we have to give the dependent variable, u of x or whatever it is. I don't know how that would, I don't know exactly how that works. U of x, y.
I'll put it in the same way the framework is made. So that would be, so initially we'd have the variables, and then we'd have parameters where you specify the subcomponents.
Well, but then the matrix then would be there, right? It's just a matrix, right? Of the coefficients of the various derivatives of this thing here, right?
Okay. So, and how would we address? I mean, so so we have a vector for the conservative convection and a vector for the convection. How would we know where to put the vector without having?
There's no vectors here. This is just an equation that is just something that is doing the generic. That's just doing the generic thing, right?
So maybe I'm misunderstanding you. This matrix.
I'm just saying this matrix is just giving you the coefficient. The coefficients in here are the coefficients of d, u, x, y, z. I mean, so let me write it out. It's derivative.
Right, okay.
Derivative of, then that would be, the components. The ijth component is derivative ij of u of whatever it is, right? It's the coefficient of that, right? So the whole thing is a sum of the matrix terms a, ij, this thing here times that, and that thing summed, over I and j. See what I'm saying?
That's just the diffusion term.
Yeah.
That's only the diffusion term, Stephen. That doesn't include some of these convection and other terms.
Well, you're saying that the aij have to depend on u, right? That's what you're saying.
In general, they can. No, I'm not saying that. I'm saying if you have a convection term, it's not a second derivative. It's just a first derivative.
Okay, fine. So you're saying that there has to, so I'm just saying that if you say there's a linear PDE term, then that's the second derivative there. So you give a matrix there. If you've got first order things, you give a vector there, right? So you're giving vectors of coefficients, right? So the thing is a sum of the pieces that are first order, second order, third order, whatever.
The issue is that there are, and this is not crucial, but the issue is that there are cases where having the C inside that divergence you're sort of giving us makes a difference.
Absolutely. So this isn't the general case, right? This is the case where, in other words, that matrix, where it goes, whether this is simply the coefficient of the, this is the mathematical form that is normally given. It's just a sum of, various order derivatives, right?
Yeah.
I think we should do this. I think it's a good idea.
Yeah, I'm not sure. I mean, in general, these coefficients can depend on the dependent variable. So I'm not sure linear term is the right.
Okay, well then you tell me what it should be. But I mean, this is you're saying it's not necessarily a linear PDE.
It could be nonlinear. It doesn't have to be, but it could be in principle.
I mean, yeah, maybe this level is appropriate for the linear case, and
well, but no, you tell me what this should be called. I mean, this is basically a sum of components, right? This is some kind of I don't know. You tell me what this is. I don't know. Okay, but in any case, this is the
elliptic PDE term.
Why is it elliptic? Why couldn't it be hyperbolic?
Well, it doesn't have to be, but that's
no. So then let's not call it that, because it isn't that. What is it? It's a
second order term. Second order term.
But it's not second order because you can have any order, because the matrix can be any rank.
Oh.
I mean, do you see?
Did you want to go that far?
Of course. You just do any rank. It's trivial. It's just the same exact formula.
Sure.
PDE term, just
tensor term.
Tensor PDE term.
Or tensor term. Either tensor PDE term or tensor term. I'm wondering whether these should all have PDE in them.
Yeah. So, So that would be, for example, acoustic PDE component or term.
I think that wouldn't be bad.
Do you also want that for the diffusion one? Like diffusion?
I think so. Diffusion PDE.
All of them PDE term. Okay.
I think so. I mean, I think so. I think that is because then we have source PDE term, and we don't have a problem there.
Yep. Okay.
Good point.
I mean,
and derivative term.
What do you think?
I think it's okay.
It's okay.
Derivative PDE term. Yeah, I think that makes sense, because then we're out of the box of is source term the right name? Because we can't have a thing called source term. Yeah, diffusion PDE term.
Yes, it's not too bad.
It's fine. Yeah. Laplacian PDE term. I mean, you're not going to use it for anything other than a PDE, right?
No.
No, they're very specific. Yeah, I think the specificity is actually good.
Now, obviously, Dirichlet condition, Neumann value, those are more generic, but that's okay, because those are, I mean, they are always for PDEs, but it's okay.
Yeah.
All right.
And those are not changing. Those were introduced many
I understand.
releases ago.
Right.
So it would be heat transfer PDE term, which is very good, I think.
Yeah, that's good.
Yeah.
A heat transfer PDE component. And by the way, this isn't model PDE transfer. That's not the right thing to use, right? So, it should say
this is not updated, I think, the PDE models page. I've changed that.
Okay, should I get an update?
Leave it. I'll fix it.
Okay, please let's not have cartoon pictures like this. I mean, if we're going to have something like that, are these ours that we drew, or are we?
Yes.
I don't like them very much. I mean, the style is too cartoonish. If we're going to have this, we need less detail in the pictures.
Okay, so what we didn't want was, there's like a picture farther down, like a plot. Oh no, some of them have.
It's in the boundary conditions pages. It's not here. Yeah.
Yeah, but I find they're super unintuitive. They're not very helpful.
No, I agree. I think this is useful to have, but there's too much. This is too cartoonish. This needs to be simplified.
Yeah.
Okay. I mean, this picture we could forget about. There's no flames here. There's just forget the hand, forget the bubbles. This is forget the beaker, forget the 3D beaker. Just a flat beaker, conduction, convection, radiation. It's fine. You see what I'm saying? Just the very minimal.
This is, I expect people to read this that don't know what convection is.
I understand.
They've never heard it. But they're going to understand it from
I
here.
understand. But this picture is too whimsical.
Okay. No, it's borderline. Yeah. But it's, yeah.
I mean, it's interesting. And we should definitely keep these pictures and we can use them elsewhere. But I think these pages should not have those pictures on them. Right? They should have much simpler pictures. Right? How can we communicate with the least sort of whimsical cartoon, stuff?
So the one on the diffusion term page was okay?
It's okay. Yeah, it's okay. I mean, just skip the representational junk with hands and things. Because, radiation works, no. We don't need that. I think.
I mean, we could test it on people. If we do something, the problem is, I mean, I'm all for trying another iteration, okay?
Yeah.
But I know when we go too abstract that we
then people
stop communicating.
Okay, but okay, just reduce the whimsy level.
Sure.
Okay, what do we need to look at next? So let me just look down here at something like acoustic absorbing value. Okay, that's useful. That's a perfectly reasonable picture. I don't have a problem with that picture.
That's probably a prototype. That doesn't look fine.
Nope, that's what we wanted to put there.
Oh. Okay.
Okay. So, all right, absorbing value. So, okay. So if I take entities, we have a bunch of acoustic absorption data. Can I just put entities here?
Yes.
Can I put?
I've added a new property to these models called material, and then you can enter the material as an entity. I've done it as a property of the parameters because then you'll only have to specify it in one place and not at every boundary condition. So if you look at the acoustic component at the main ref page, you'll see a new property added.
By the way, this I don't have a problem with. Again, I just don't like seeing hands and beakers and things like that.
Okay.
This looks good.
Yep, good.
Even the speaker there is sort of okay. I mean, that's sort of okay. Go ahead. What were you going to show?
Okay, scroll down a little bit. There's a list of properties there. There's now a new property material. And I think in the scope section, there is an example of where I show that, where you specify a material.
What does the blank mean here?
Blank means there is no default material.
Then there always should be a default. It should be none or something. Or automatic. What is the default material?
None. There is no default. The default is that the density are set to 1 and the sound speed is set to 1. So because density and sound speed.
And say it be automatic. Then call it automatic.
Yep.
None would mean a vacuum, which doesn't work very well.
Yeah, that's not right. Right. So and if you scroll down a little bit, I think in the scope section, there is
parameters, sound speed. Okay, so let's take a look at this. So then here I see parameters. So instead of parameters, I could put in here air.
No, you cannot.
Why not?
Just hold on a second, because you'd add to parameters, you add material. String material goes to whatever material you like.
I don't believe in that. Yeah, go ahead.
The reason why this is useful is because you have several components where you need to specify this, and parameters is the place where all information is collected.
Okay, but right here you've just got material properties, sound speed and density, right?
Yes, and you could replace that with material goes to air.
No, I know, but why not just put air there? Because you can always get sound speed and density out of the material object. Do you see what I'm saying?
But then it's not. I mean, it's not an association anymore. Then it's
that's
just
okay. It's okay. Then you have a very beautiful thing here. What you're saying is, right here, wherever you give this acoustic component. Instead of pause, it just says, I mean, this is very beautiful. That what you would be saying is something where you would say something like, if I go to a page here, okay. Isn't that magnificent if you could just say that, right? Acoustic components are not working.
But we still need the parameters, for example, for the boundary conditions. So
I understand, but you didn't give them here. You didn't give them in this case, did you? Right, you just said pause is this. Those are pure material properties.
Okay, so in the cases where it just works by chance, so to speak, or not chance is not really the right putting, but
no, I agree. If you need to give other parameters, then you've got to give other parameters, and then you say material arrow, whatever, and then from material you pick up these other things. But what you listed here, okay, so here, density of media, sound speed, fine. What is monopole source and dipole source?
So these are components or subcomponents of the PDE model. You can add monopole sources or dipole sources to this model, and the default is to not have them. So
but where are they? What's their spatial position?
There, so above it says the time domain acoustic model is this and that, and then you have two equations, one for the time dependent, one for the frequency domain, and there you see F and Q, which are the dipole and monopole source respectively.
Okay, so but what's the position of the monopole source, for example?
It can be anything. I mean,
no, but I understand what the setting for the monopole source is. Just a value of the source, right? That's the value. That's the intensity of that source. If I say monopole source is 3, where is the monopole?
Then it's all over. Space. Then it's everywhere in the domain. If you want it to be a specific.
Oh, I see. I got it.
If blah blah blah.
Yeah, I got it.
Yeah.
So,
everything that's active is always in the entire domain. If you want to restrict it, you need to specify.
Okay, I get it. So these parameters represent features of the whole medium. So in a sense, there's a medium where it's wobbling. It has a monopole wobble everywhere, so to speak.
Yes, if it doesn't really make sense, but yes, that's what it would be. Yeah.
Well, why doesn't it make sense? I mean,
because a monopole is typically an object that is spatially constrained.
I know, but so how do you do that in this case?
You say if x smaller than this and that circle or something like that, then it's 1 there and 0 outside of it.
Okay. So I don't quite understand why you wouldn't be giving. I see. So that is an if statement as opposed to a Dirichlet condition, a Neumann condition, or anything else.
Well. So now we're mixing things. So we're now talking about the entire PDE, which is valid on the entire region. Dirichlet and Neumann is just boundary. It's just interface.
No, I get it. But so the point that I'm making is what you have here is a new construct, right? You have a thing where there is a value within a region. Right, that's the concept that you have here. If you're having those if statements, you're saying if x, y element of some region, which I don't think will work. How would you do that? How would you say if x, y is an element of an ellipse, for example? Would that work for the monopole source?
Yes, yeah. But that's not how you do it. Yeah, but it's not how you do it. It's not efficient.
How would you do it?
Well, you just specify the region symbolically. Like x squared plus y squared is smaller or equal to 1 or something.
But why? Why? I should be able to give it, if I've got some complicated piece of computational geometry that I've got, x, y element of some intersection of some, something formed from a union of whatevers. Yes. Why can't I specify that?
You can, but then so Stephen, we want to be able to do this in large scale for really large scale problems.
We also want to be able to do it for small scale problems easily.
Absolutely. And
okay, we need to not forget that.
Yes, if you want to do it for small scale problem, you can do it exactly the way you want to do it. It works. It's just not going to be efficient. I'm just trying to say this is not the ideal way for large scale problems.
Oh,
but you can do it that way.
You can tell people that. I mean, okay, but so by the way, a question from Vladimir on a live stream is about, does it work symbolically and numerically? Absolutely. Absolutely. When it can be done symbolically, we should be pretty strong at doing it.
Yes.
Is
so
that true?
if you in the diffusion term example on the right-hand side. If you remove the kappa goes to X or something, you'll just get a symbolic expression.
Well, we have kappa. Well, here, I mean, this case here, if I say
so that's a symbolic version as well, yeah.
Yeah, if I say desolve %8
equal to 0 or something,
and solve it for u of x, solve it for u there, with x as the independent variable, right?
Yeah. There you go.
Okay. Okay, so let's go back over here. All right, so is there anything else in terms of, I mean, I think we've been going through, yeah, I like this with the PDE thing in there. I like this a lot. I mean, load PDE term.
That load is not the actual, it's not the current name, it's source term. That's an outdated.
Oh, okay, fine. All right, okay, fine.
It's going to be source PDE term then.
Okay. Okay. Now, obviously, it bothers me that units aren't going all the way through here.
Yeah. So there's a small update, and so what you can do now is you can use these PDE models with units. They're going to be converted to SI based and then going to be stripped.
Okay.
And we're working on the stuff for making it work properly for following release, but it's not going to happen for 12.2. But yeah.
You know what? Why don't we do this? If we had an option that was some kind of unit conversion option, then we could at least describe what we're doing. That is, if we have a unit system, right? Let's say it's SI, for example. We could, there's nothing really in your code that really cares whether it's, turning to SI-based units or imperial-based units.
Absolutely not. No,
right.
There's nothing that cares. Yeah, correct.
Right. So if we had an option, what do we have? We have a unit
in
system.
In principle, what you want is you'd like to specify the target units. But the only thing, yeah, so that's easy to add.
Okay, well, so look, we have this option, unit system, right? Which we could use, which we could put in here to say unit system arrow whatever. And what it could do, I mean, that will be useful anyway, even if we're actually returning units, okay? So then what I think we should do here is we should say something like, for now, we should have unit system go metric arrow none, or some such other thing, which means, I'm not sure that's quite the right phraseology.
Yeah, but that would means, be the default now.
Right, which means that, because in general, we're going to have to convert to some definite units anyway, right? And I mean, yes. Unit system arrow automatic will try and be clever and look at, because like if you're mixing inches with meters, right? What are you going to convert to?
I don't know. I mean, basically.
Right, but that's why we have a unit system function. Right. I mean, the unit system option. And then what we would do is we would say unit system arrow automatic will look at the equation, and if everything is an imperial, it will convert to imperial-based units, etc. Right? But that's for the future. But for now, we can just burn in unit system. I mean, you don't really care if it's metric or anything else, right? So long as it is a valid unit system target, then you're happy with that. Now the issue is, how do you specify the fact that the units will eventually be stripped? I think that something like metric arrow none, you might want to ask the units team whether they have a preference for how to do this. Explain what the issue is, because I think then we have so long as we set this as the current default, we'll be fine. Changing it later to just be automatic.
Good.
Yeah, that's really a good thing, because that way that way people can give dimensions in inches and nothing will go wrong.
Yeah.
Okay. Nice. All right. Let me just go back here to look at this. Now, let me look at, I haven't really dug through the details of these. I mean, like if I go to, let's go ahead.
Look at the diffusion term. It can do complicated stuff. If you go through the examples, you might be intrigued, I think.
Okay. All right, but let me go through the documentation first. Represents a diffusion term of that form, diffusion coefficient C. Okay, so you should explain somewhere that obviously C can depend on X.
Yes, it's further down. It's explained in the ref notes.
What do you mean by in context with other PDE? I don't understand that. Oh, I see. Wait, I don't understand that. I don't understand this statement here. What does that statement mean?
So this is the form we've talked about earlier that we're converting to.
Okay, but when it says in context is given by, but there's an alpha and a beta and an A here, which are not being specified. So I don't understand what this is. You have to say what the alpha, beta, gamma are for the diffusion case.
So is it so this how to ask this? So you see that part of the equation is grayed out. That isn't enough visual.
Oh, hell no.
Information. Okay.
No, I did not understand that at all.
Got it. Yeah.
Okay, so then I mean, if you put a box
I'll think about
around
something else. That's fine.
Yeah. No, that's fine. Put a box around the terms that it should represent or something.
Yeah. Okay.
Or put a color background or some such other thing. I didn't get it. I see what you're doing there. I mean, or just say explicitly, you know, the whatever. I mean, yeah, I like what you're doing there. I just didn't understand it.
Yes, good. That's why we're here.
Okay. What the hell is orthotropic? I never heard of orthotropic.
Well,
what does that mean?
So it means that the diagonal coefficients are not the same. They vary.
Oh.
So the XX component is different from the ZZ component, for example.
Okay, so that's like a material that has, you know, cubic. Wood. That would be a cubic material.
Wood is orthotropic.
Okay, but it has to be. I see. Okay, there has to be orthogonal directions that are, and there are no cross terms. Well, this is nice. Yeah, and again,
the same thing. Yeah, yes, sure, understood.
Somehow.
Yeah. So now in the scope section, we'll build up complexity. And
you got to show how these work with activation.
Yes. We've discussed this. I'm going to do this.
Yeah. Okay. Fine.
Yeah. So there now you start to see how things look like when we have several dependent variables.
Where are the several dependent variables?
So we have U and V as two dependent variables. And now the
coefficient, here, yeah.
Yes, and the coefficient now becomes a tensor.
This is nice. I'm a little bit confused that you're talking about a Poisson equation here, given that there's already a Poisson term.
Yeah, I mean, I'm trying to show that you can use these terms to build up larger equations.
Fair enough.
So there you
have. This is very nice.
There you have an orthotropic equation. So the diagonal is 110.
Yeah, I get it. Yeah, so it's a smoosh thing, and it isn't. So it's an e to the minus x squared plus y squared, with the alpha x squared plus beta y squared. I mean, it would help me to see that symbolic solution, I think, in these cases where there is an easy symbolic solution.
Yep. Okay. Yeah, good.
Why is it so wiggly?
It's basically
it's 10 to the minus 16. It's basically 0. It's numerically 0.
I don't know why
you want to really in this section. That seems wrong. Don't show numerical noise. That's like showing. You can show that in the possible issues section or something.
Okay.
Well, this is very nice. Let me look at one more, some much more elaborate case.
Maybe convection or elaborate case. Okay. Look at heat transfer component. That's another one I'm quite happy with.
This has come out good. This is very nice. Heat convection velocity. Oh, I see. That's the convective term.
Yep.
We do not have any emissivity data.
Yes. I filed a bug for that, so it would be nice to have that.
I'm sure we can get it. I'm sure we can get it. Just ask somebody to get it. I mean,
it's filed as a bug, yes.
Mm-hmm.
And I've also refiled that. It would be really nice if we have a material data entity. Yeah.
That's been an issue. I mean, we have material data, as you know.
Yes, but not as a proper entity. It would be nice to have that.
Yeah, it'd be very good to have that.
Yeah.
Yeah, you should.
That's
a complicated discussion with Michael, the complicated stuff with sources and so on. But I think we should be able to just solve. I mean, given what you've done here, it makes sense to do that now.
Okay.
Without this, it's it's like, okay, it'd be nice to have, but nobody's going to use it.
Yes.
With this, people are really
I'd be a customer of it. You can be sure of that. Yeah.
Right. So let's make that point then, and we just start. We may not have every type of ANS alloy or whatever.
That's fine.
Initially,
that's some basic material.
Progressively get it. We should be able to get it.
Yeah.
Okay. Just tell them you care.
Okay.
But I think you're going to need to talk to them in person to make the point.
Yeah. Good.
And show them some of this stuff. Show them why you care.
Yeah. Good.
Okay.
I plan to do that anyways for the units group to show what I've done so that they can give better feedback of how it could work with units. So we'll do that in one go.
Okay. Now I assume these names like specific heat, those agree with the property names.
They agree with the names. I've double checked that.
Okay, good.
We've discussed this last time.
And by the way, you also should allow an entity property entity here. One of those entity property objects on the left-hand side of the association.
I don't know what that is. Entity
property.
Okay,
so if I say that. So you should allow, in your association, you should allow somebody to say specific heated STP, arrow, whatever. Or actually, I don't know, you need to ask them how to do this.
Okay.
This particular, this is the wrong one because this is for an element. Again, you need to ask them how to do it. But I'm saying that you need to support being able to have, because the reason you need to support that is because you can get an association, a property association out of the entity, right? So if I say something like, control equals tungsten, okay, and then I say property association here, then I will get, hopefully, this is the prototype build, so who knows what I'll get here, but fundamentally, I'll get something like this, right?
Yeah.
And so being able to take a piece of this, right, and just feed it into your thing would be good.
Wouldn't that be covered with the entity anyways if it just gives tungsten as an argument?
Yeah, it should be. But I think just for niceness, you should support this case.
Okay. There you have an example with the material. That's how it's done now. But it's
nice. That's not bad. I mean, you could leave it out. You could just say tungsten. It'll be cleaner.
Okay.
And so each of these would then take, okay, let me just see the fanciest thing. Did we get the spoon yet? Famous spoon.
I remember the spoon. I'll add it, but it's not there yet.
When was that? It was like 2010 or something? Or
yeah, it's a few years back now.
Right. I saw Oliver in Germany, and we were talking about PDEs, and I was drinking some random drink, and it had a spoon. And it was like, when we'll be able to model the spoon.
I see. Okay.
We're getting there, right? I mean, we
can do it now. It's not a problem. It's not a problem.
Okay. All right. Okay.
Yeah,
you can.
That's fine.
All this visualization, all these slice plots were basically, they will come in handy here. They were using them in symbolics too for PDEs a lot.
Yeah, this is really nice. Answer to Bob's question on the live stream is make it a data set, then it will come out. Then if you make this thing, if you just say data set, it'll display in a table. Okay. Okay, is there anything else we should cover in this discussion?
Do you want to talk about the monographs accompanying these tutorials and stuff? Is that something that interests you?
Well, it interests me, yes, but are they written?
Scroll up all the way. So if I'm not sure it's going to work in the prototype build.
Look at the guide page, Stephen. You can see at least, but there's something you will have an opinion about. Okay, look here.
I saw that. I saw that.
So okay, so this is slightly non-standard. I do think it's the right thing compared to tag them on at the end where nobody will find them. I know it's
I'm not sure this is quite the right style. I agree with the principle.
Yeah. So do you have another idea of how?
So the style was suggested on TNU docs. So I've asked how to do it, and that's what they suggested would be the least invasive, so to speak.
It's not terrible. It's not terrible. I mean, I'd like to see the final design. Do I link to it? No, it doesn't.
You need to right click on it and copy the link and paste it into the browser, into the help system. Sorry, because this is a prototype. It's not gonna start directly.
What do I want to do?
So,
I need to go to another meeting.
Okay.
Let's do this another time. Yeah. How long is this monograph?
Long.
Like 200 pages?
Not that long, but I don't know how many printed pages, but it's longer than the average monograph we have in the system.
Are we going to print them?
We hadn't
never thought about it.
I think we should consider it. I mean, would we have a decent collection of differential equation, sort of a book about differential equations that has these pieces?
I mean, we have acoustics, heat transfer, and mass transport, and I plan for every physics domain I add, I'll have a tutorial as well, and that explains the derivation of the equations, the boundary conditions in more detail, and all that sort of stuff, and shows different types of examples than what we show in the reference pages.
So, I mean, I have a question. In people's use of this, somebody's going to say, I have a spoon, for example, and I'm trying to model, stress in the spoon.
Yeah.
Whatever, right?
Yeah.
What we really need to give people is use the notebook paradigm to give people essentially computational essays that show this is how to do stress analysis in the spoon. So that's in the monograph.
No, we have more than that. Could you just quickly open the help system?
In here.
Yeah, just open the documentation and search for PDE models or something, PDE models overview. This search system is really driving. Try to write it in one word without the space, sorry.
PDE models like that?
Maybe that. Yes, there, click on that. Okay, so this is the collection of tutorials, and each tutorial has, so we have a tutorial.
What is a tutorial versus a monograph?
A monograph. So those are monographs. So so these are models that we have that are in depth of how to do a specific model, and the purpose of these new terms and conditions and whatnot is to replace the coding of the equation.
So these get simpler, Stephen. With this new modeling language, these get
Oh, simpler. I see. These are things that already existed.
Yeah, yes, we wrote these first, and that's where we...
That's how we learn.
Okay, so all this junk will go away.
Yes, will go. Everything will, all of that will go. That's the point of it.
So people so far have been using these to solve these things for the raw equations.
They copy the junk part and use that in their own notebooks. That's how they.
Okay, so you're saying this is being replaced by something nice and clean. Well, that's very good.
Yes, that's the plan for this. Yeah.
Okay, and the computational geometry flows well into all of this stuff. Is that true? In other words,
I mean everything
Yes.
that I need. Yes, yeah.
Yes, and there's more coming. I mean, these are synergistic. As geometry evolves, there's easier to do PDE modeling, whether you're importing models from a CAD system or you're modeling it from the ground up and so on. All of that gets easier over time.
How long have you been working on this, Oliver?
10 years, almost.
Okay, well, it's impressive.
Good.
Okay, all right, and I mean the roadmap from here.
It's clear. So basically, unfortunately, our marketing department doesn't really have information about what our customers request or need. So I did my own kind of survey to try to find out what people want. And from there, I have a ranking of what finite element functionality is most needed now. And that's what I'm going to implement. At least that's the plan.
Those are, I mean, these are other domains. So you've got things like heat transfer and so on right now, and you have other domains you're planning.
Right. So I mean, sorry, that's a bit misleading. So I mean, for the most missing domains for physical domains is structural mechanics and fluid dynamics.
Yep.
I was more talking about more general new finite element functionality that I'm going to add.
What's it needed for? The new finite element. Well, I mean, what are domains? So, for example, if I were to do, I mean, structural, structures and fluids. Yeah. Clearly, we need those. Yeah. But I'm asking the question: what? I mean,
what are the other things?
Yeah. I mean, like if I want to solve a black hole merger, for example, right? Which obviously, where the equation setup is very complicated.
Okay.
Right. And where people do that routinely using our tools. And in principle, we could have an Einstein equation, Einstein tensor term, Einstein tensor PDE term.
Yep.
I mean, it's just 4 dimensions, and it should work. I think in the end, people are turning these things into essentially finite element methods. Although there's some, the time-dependent stuff. So you have plenty of time-dependent equations here, right?
Yes. Yeah.
Sure. I mean, it's a good exercise. If you ask Jose, he has been in the business of, supporting, solving equations in general relativity. Okay. Mm-hmm. It will be interesting to see whether you can flow through from his exact tensor manipulation system directly into your PDE system.
Okay.
See what I'm saying? I mean, by the time we can do a black hole merger in sort of, 20 lines of code, then we know we've arrived. Right? I mean, that, I think, I mean, we should ask Michael Trott for his input on what domains he thinks people are going to care about. I mean, like, for example, in this whole pandemic time, there have been a bunch of PDEs solving, with some of which done with our tools. But the question is, what domains, are there obvious domains there?
I mean, speaking as an engineer, there's other domains like chemical engineering or soil engineering and stuff like that. But you're talking more about physics related stuff.
Well, reaction diffusion equations are an obvious one.
And we have those, so that's fine.
Well, but you don't have a reaction diffusion term. You don't have a reaction term.
Yes,
you don't have a reaction.
We have a reaction term. We've just looked at that. I mean, it's on the reference page.
What's it called?
Reaction term.
Great.
Yes.
Well, it's the reaction PDE term now, right?
Yeah, well, right. Yes, that's what it's going to be renamed to. Sure.
Yeah,
sure.
well, great.
And
fine.
Then it's just a matter of combining the two to have a reaction.
What section is that under?
It was on the guide page.
I know, but what section of the guide page was it in?
Very first, top.
Oh, okay, great. All right. Okay, terrific. That's the best answer.
Yes, good.
So you should make, in the examples, you should make some of these Turing pattern things and so on.
Yeah.
From reaction diffusion equations.
Yeah, I have an example for that. I can put it there. Sure.
Okay.
Great.
Do you
want to see this stuff again? Or is it?
I would like to. I would find it interesting. Yes, I think it'd be worth doing one more of these when you think it's all really final and when it's in the head branch builds and so on.
Okay, good.
And I wouldn't mind seeing the monographs when they've been turned into, I mean, you already have the monographs cleaned for the new design or not?
That's going to take a while, but I can ping you before release or something like that to have another.
Sounds good. Yep.
Yeah. Great.
Great. Okay. Very nice work. Good stuff.